Last time, we saw how renewables reshape the energy system. As we layer in solar and wind, net load drops at midday and the curve takes on its duck shape. When the sun fades, the evening ramp steepens and the marginal unit moves up the stack. Prices fall around noon and spike at dinner. So what actually flattens both the midday dip and the evening spike? The answer is flexibility. Battery storage absorbs excess energy when prices are low or negative and releases it into the evening peak when the system is tight. In this lesson, we will explore how BESS flattens the duck curve and narrows the spread between midday lows and evening spikes. If you would like to follow along, click the link in the video description below, hit free preview on the course page, and after creating your free account, you can download this model for free and explore it yourself. If you haven't already, open the Excel file you just downloaded for this lesson. BESS inputs are fully controllable, so you can adjust duration, power, and efficiency, and watch net load and prices respond in real time. Before we jump into Excel, a quick recap. Net load equals total electricity demand minus solar and wind generation. Start with everything consumers are using across the grid, total demand. Then subtract what renewables are producing in that moment. What remains is net load, and that's what climbs up the merit order and determines prices once renewables are exhausted. Now let's add storage into this balance. Net load now becomes total demand minus solar and wind plus BESS charge and minus BESS discharge. We still start with total electricity demand, everything consumers are using across the grid. Then we subtract what solar and wind are producing in that moment. Next, we add BESS charge. When the battery is charging, it behaves like load. It draws energy from the system and pushes net load up. So during sunny or windy hours with surplus power, charging raises net load. And when the battery discharges, it does the opposite. It acts like supply and reduces the net load the grid has to serve. This is what lets storage shave the evening ramp and smooth out price spikes. The key idea is that the battery doesn't create energy. It shifts energy from one part of the day to another, with some energy losses from round-trip efficiency. Now that we have defined the balance, let's switch to the 24-hour chart and watch what happens when we turn the battery on. As in the previous lessons, we are back on the 24-hour view. Solar and wind generation are on. Net load dips at noon and ramps quickly into the evening peak. Prices follow the marginal unit, low at midday, high at dinner. Now let's turn storage on. This configuration is already tuned for the system we are looking at. 5 GW of BESS power and 4 hours of duration, enough to meaningfully cover the midday surplus and the evening ramp. Watch what happens on the chart. You will see charging during the solar peak and discharging as the demand rises in the evening. Notice the effect on a blue net load line. The midday trough lifts, the evening peak falls, and the price proxy narrows. Same total energy, just move to the hours when it has more value. Now let's see what happens if we cut power in half, from 5 GW down to 2.5 GW. Storage is still charging at noon and discharging in the evening, but the effect is barely noticeable. The curve is still steep, evening prices are still high, and volatility remains. Why? Power defines the rate at which storage can move energy from one part of the day to another. If the power rating is too small, you leave most of the surplus energy untouched. If you're finding this video lesson useful so far, we would really appreciate if you would like this video or subscribe to our channel. That helps us to make more of these deep dives. Quick definition before we test our next input. Duration is usable energy divided by power. Megawatt hours over megawatt. It tells you how long the battery can sustain its full output before it's empty. We will unpack duration, energy to power ratios, and sizing trade-offs in much more detail inside our BESS D-Lab. But for now, let's see what happens if we keep the same 5 GW power rating but cut duration from 4 hours down to 2 hours. We're looking at the same power but half the energy. Watch what happens. The battery now finishes discharging before the evening ramp is over, and it finishes charging too early in the midday period. That means parts of the curve are left uncovered, and you start to see small spikes once the battery is either full or empty. Duration defines how long storage can help, not just how much power it can deliver in the moment. If it's too short, you can still shave the curve, but you can't flatten it fully. Now let's return to our 5 GW and 4 hour baseline. A few comments on inputs before we move on. Round-trip efficiency is always below 100%, so the battery gives back slightly less energy than it takes in. These are state of charge limits, the minimum and maximum state of charge. They protect the battery from overcharging or deep discharge. We'll leave these inputs untouched for now, but they're critical in real operations. But let's look at what happens if we start the day with a nearly fully charged battery, 90% state of charge at midnight. As demand ramps up in the morning around 6 AM, the battery begins to discharge. But that early consumption isn't enough to bring the state of charge down far enough before the solar peak arrives. You will notice the battery doesn't have enough room left to charge when the surplus hits. So the midday trough isn't fully covered and prices still dip. This highlights a real operational challenge. Storage only helps if you have created headroom before the surplus shows up. Determining when to discharge so there's room to charge later without wasting opportunity is a non-trivial control problem for system operators. Back to 20%. Now there's sufficient room to charge at noon and energy to release into the peak, exactly the shape control we want. A quick recap. Capacity dictates how fast you can move energy. Duration dictates how long you can sustain it. Efficiency and state of charge limits define how much you can actually use. Get all three aligned with the price shape and storage flattens both net load and prices. Now that we have seen how batteries reshape net load, let's recap from our previous lesson and place storage back into the broader system in the context of the merit order. From left to right, we move from low-cost renewables to mid-cost thermal plants to high-cost peakers, and finally storage. Unlike fossil plants, batteries don't burn fuel, so their marginal cost is extremely low. The only variable cost is cycling losses and degradation, which typically land in the $5 to $20 per megawatt hour range. That's far below the fuel and startup cost of a gas peaker. Functionally, storage shifts energy. It charges when prices are low or renewables are abundant, and discharges when the system is tight. But it's important to remember, batteries are almost always energy limited. Duration, not nameplate power, determines how long they can stay in the market. And this is where batteries stand out. Instant flexibility. They can reverse direction from charge to discharge on command. That makes them the most responsive and flexible asset in the stack, especially when prices move fast. Before we move on, let's quickly revisit how a battery actually connects to the grid, because everything we have modeled so far only works if this chain is in place. On the right, we start with the battery itself. The cells store energy in DC form, the same kind of power you would find in a phone or electric vehicle. To charge or discharge into the grid, we need a bidirectional inverter, the power conversion system. It converts grid AC to DC when charging and DC to grid synchronized AC when discharging. That AC power first passes through a transformer which steps voltage up or down, depending on whether we are absorbing or delivering energy. Finally, everything ties into the distribution grid, where the battery either behaves like a load when charging or like a generator when discharging. Let's close by stitching it all together with solar and storage. Solar panels produce DC power. In one path, that DC can go straight into the battery to be stored. Or it can run through the power conversion system, where it's turned into grid synchronized AC and sent out immediately. Later, the flow can reverse. The battery discharges DC and the power conversion system converts it back to AC. That AC then goes through the transformer to the right voltage and into the distribution grid. The payoff is the same idea we have seen all lesson. Shift energy, charge when solar is abundant and prices are low. Discharge into the evening ramp when the system is tight. That's a full loop, solar, BESS and the grid working together to flatten net load and normalize spot prices.